Hello everyone, I'm Ibrahim and I'll be presenting to you whole body MPC on dynamic occlusion avoidance, a maximum likelihood visibility approach. The problem at hand is visibility for robotic applications. Visibility here stands for the existence of a line of sight between the robot and the target of interest. And it is a necessary condition for vision-based tasks such as detection, tracking, and manipulation. Whenever this visibility is lost, the confidence of the feature tracker in the target pose deteriorates due to drift. So ideally, we would like to achieve robot motions that avoid shadows cast by occluding obstacles. In order to do that in an optimal control setting, we need to define notions of visibility and obstruction in a way that is suitable for gradient-based techniques while accounting for uncertainties and sensory noise. Currently used methods in the literature are inadequate to achieve our desired goals. For example, we may use visibility constraints, but those come at the cost of limiting control to a camera's field of view. Meaning, whenever the target goes out of the field of view, control has to be halted. Other methods do this separately from motion planning, but this entails increased workflow complexity, and those methods are still rather immature in terms of efficiency and efficacy. In this work, however, we propose achieving occlusion avoidance by maximizing the log likelihood of visibility over the time horizon. Such a maximization may be directly augmented within the main cost function, which includes whole body dynamics as well as system costs and constraints. The likelihood of visibility, however, is rather obscure, so we propose our own novel dynamic programming algorithm called shadow field, which uses LiDAR or RGBD data in order to compute this distribution of the likelihood of visibility over the space of interest. As a matter of fact, what it does, it gives us smooth and continuous shadow approximations. In this scenario, we are comparing the soft shadows computed with our algorithm against the hard shadows defined for the following obstacle with the two blue lines along x equals 70. Extending to the 2D case, we demonstrate the shadow field mesh in a 2D environment with a light source dynamically moving between occluding obstacles. We see the resulting shadow field mesh exhibiting the same continuity and smoothness characteristics highlighted for the 1D case. For the 3D case, we perform real-time shadow field mapping using ALMA hardware. For visualization purposes, we only show in a top view a slice of the shadow field that resulted from our mapping. At the center, we show the light source. We have the occluding voxels and color scale. We have the shadow field slice in grayscale. And finally, the Velodyne sensory data as white dots. We see the shadows exhibiting both umbras and penumbras. Now that we have everything, we demonstrate the validity of our approach on ALMA using physics-based simulations. We are visualizing here the shadow field slice at the end effector level, and in a game of hide and seek, you see our robot finding the least shadowy path and establishing complete line of sight with the target of interest, which is hidden behind simulated obstacles. It is noteworthy here that the motion is solely driven by the cost arising from the soft visibility constraint, and we couple it with an orientation constraint, which fully locks the end effector orientation onto the target of interest. This concludes my presentation. Thank you for your time, and if you have any questions, let me know.